Thanks a lot, Robin. And before I start, I want to give a shout out also because this is a joint work with Nina and Robin. I had a lot of fun working with them on this. What I'm going to present today is called SAGE, and it's a sampling aware global evaluation benchmark for SDMs. So this time it's going to be into the evaluation straight away. I know we end up there anyways, but yeah, let's start with it also. Also, I know you all know SDMs, but still I want to start with a quick paving the floor because this paper really started from kind of the struggles we found in the basic pipeline of SDMs. So yeah, we all know for species of interest, we grab all the occurrences we can find, we get the predictors, and then we try to fit a model to this. And then we evaluate our model's performance against expert-derived labels for this location. So we have a list of presences and absences, and we check how well the predicted probability of occurrence for that species aligns with these expert-denoted lists. And then we also know the procedure. We can not only train one model, but we can train multiple models. And then from this, we get a benchmark or like a comparison table, and we can pick our model that performs best for the species. However, things get a bit more complicated as soon as we move to multiple classes. And yeah, this is really still a simplified idea. So we have either multiple models predicting multiple species, or we have a joint model. And then we compare these models. And I think what all of us have seen before quite a lot is that they all kind of reach similar performances. We are talking about really small ranges, and it's really hard to disentangle what is really happening inside the model. So we can hardly tell apart if the blue model is maybe beneficial for the first tree, or if it's exactly the other way around, because both of these setups would lead to the overall same OROC score. And so we know this is kind of prominent in any multi-class setup, but for SDMs it's particularly important because in the end we model thousands of species at the same time, especially in the last years. These numbers have been growing and growing. And so for 7,000 classes, it's really, really hard to understand what model is beneficial for whom. And then on top, we're in a setup where some species matter way more than other species, and we really need to know how species perform under which model. And this is paving the ground for the work that I want to present today. It consists of 3 pillars. So there will be yet another global benchmark for SDMs. I'm going to explain in a second why we needed a new one. The core of the work is a sampling aware evaluation framework that is trying to make a bit to kind of work on the corsity of this evaluation and bring a bit more light behind how species are performing under which model. And lastly, we also really wanted to bring together kind of all the models that are around in the field and really bridge between the standard SDMs and the deep learning models. So we threw a bunch of common models from both domains onto this evaluation framework. So let's start with the data set. I said we really needed a new one because we had 3 main constraints that we thought were really important. The first one was that we wanted the data set to be as global as possible, simply because like deep learning claims a lot to help with the scalability. And so we also wanted a data set that is as like global as possible and really undergoes a lot of different data and sampling regimes where kind of all the difficulty is in there. Second, and this is like kind of the hardest to find, is that we want the species identities to be disclosed. Often there's like privacy reasons, or like the data aggregation is so costly that people don't want to disclose the species identities. But at the same time, we hear more and more people integrating biotic knowledge, and also for knowing which species are truly rare and like worth for conservation efforts. We really said that we want to know what species we're modeling. And lastly, we decided that we want to work in the setup where we train on PO solely and we test on PA solely. So it's a design choice we made, but we really wanted to check, again, the scalability potential of deep learning when it comes to having really, really noisy training data and kind of the closest we can get to trustworthy evaluation data. And what we found kind of fulfills in all these constraints and tick the boxes is the presence absence data set as plot open. I'm sure many of you know about it. It's plants only. It's as global as possible. At least we have data on every continent. It's still very biased. And we paired it with like all GBIF occurrences we could find for the species that are in this benchmark. So what we did is we gathered all the GBIF occurrences. We decided that we only want to train and evaluate within the range of the species. So this already discards a lot of these issues of global extrapolation because we really decided, okay, we only care about the range where we know that the species exists. And with plants, it's really nice because Plants of the World Online has a complete list for these data set, at least of range masks. And then we run like the common cleaning pipelines to make the GBIF data usable. And what we end up with is this data set. On the left, you see the training data distribution. On the right, you see the test distribution. And clearly there's heavy biases. I mean, that's not surprising. But yeah, it's as global as we could find with the data that we had at hand. And we see it's close to 6,000 plant species. And what we made as a design choice on top is that for training, we allowed every species that has at least one occurrence to kind of also explore the deep learning long tail of things. Whereas for evaluation, we stuck with the ecology standard of having like 30 presences at least to ensure that the statistical evaluation of the model is really trustworthy.
Is the set of species by construction identical?
Exactly, it's exactly the same. Like we only kept species that ticked all the boxes for all of these design choices we made. Like of course you could enrich the training data with a set of species that goes beyond. It's just we wanted to kind of constrain it to this first and then go further after maybe. So that's the data set. But then, we still have 5,700 species. So if we compute the average OROC, we don't really know what's happening. So the core of the work is actually the sampling-aware evaluation framework that we came up with. The main idea was that we aggregate over species, but in the end, we have a lot of properties that we maybe care about more. And so maybe we want to stratify species based on these properties to kind of put them into bins together that share certain properties and then know something about their performance. So what we decided is, since we're working with GBIF data, it's very interesting to look at the sampling biases that we know are very prominent in the data. And so we looked at our presence-only points. And if you put a 1 by 1 kilometer grid over the globe, you can deduce two simple information from this data. So what you see in blue is any cell where at least one person has gone to scan any kind of species. It's a binary measure of did someone go here and collect some data, or did no one go here? And then in orange, for every species of interest, we can see, okay, where was this particular species really sampled? So that would be the orange points in here. And then what we can do is we can project every species range onto this map, because luckily we have them for all of the species. And that's how we break the symmetry of kind of the global sampling effort. And we really look with respect to the range of this species, how do these two properties behave? So what we derive as a really simple measure is first sampling effort, which is just the percentage of cells within the range that was visited by at least one person. And then second, the relative prevalence, which expresses out of all of these visited cells, how often was our species of interest observed. And what we can do with this is rank species based on these two properties and span a two-dimensional space. So what you see on the x-axis, we have the sampling effort, and on the y-axis, we have the relative prevalence. And since the two properties are roughly uncorrelated, actually, we can then group species into 4 bins that carry roughly the same amount of species. And these 4 bins express very different properties that the species undergo in the trained data. So what we have in the lower left corner here would then be species whose ranges are really sparsely sampled, and on top the species almost occurs never. Whereas on the upper right corner, we have species whose ranges are really well sampled, so we have a lot of data doing training. And on top, the species is kind of not washed out by all of the background that we have, but we have a lot of occurrences of the species. And that's kind of the space that we move in. And then we can sort every species into the space and thereby find groups that have shared properties. An example of this, so here we have an example for the lower left quadrant. The species has so little sampling effort that it's hardly visible without zooming in a lot. And then on top, we have only very few occurrences. So you see in percentile rank, it is ranked 12th in sampling effort and 35th in relative prevalence. And with that, the species ends up in what we would assume the hardest to model quadrant, which is the lower left one. And then the opposite is the species in Taiwan. Taiwan generally is really, really well sampled. So we have a lot of sampling effort in the entirety of the space. And on top, the species is very, very prevalent or really attractive to be scanned, or we don't know the causes for this. It's just data properties we see. But with that, it ends up in the upper right quadrant where we would expect the models to perform best simply because they have a lot of data at hand. And so what we did then is just throw all the models that we could find onto this data and the evaluation framework. Here, I just decided to show an excerpt. So for the non-deep learning-based models, we also evaluated max-end and the rebalanced random forest to get a fair comparison on how well is the standard methods already are performing. And for the DeepSDM side of things, we have a really simple MLP-based baseline where we don't do a lot of data subsampling or anything. We just take the data cleaned as it is. And then we have an optimized DeepSDM baseline where we play around a bit with the architecture, the laws, and we do some very simple debiasing strategies, nothing very fancy, just to see a bit, okay, if we're not fully naive, how far can we get? And what we find is that the random forest is the best out of all the single species models. And what is even more interesting is that actually it outperforms the optimized deep learning model. And I mean, we're here talking about like the really, really simple setup of only tabular data, kind of really the standard SDM setup. But in this, what we find is that actually the performance gap is not so large. We also looked at training time. And also this, I think, tells an interesting story, because if you can get your hand on a GPU, actually training jointly for almost 7,000 species is quite efficient. Whereas for the random forest, of course, you have to train 7,000 models. So it kind of accumulates when you have to do all of this work. But when it gets more interesting is if we really look at the metrics in the space that we created. So what you see here is the comparison of the optimized DeepSDM versus the random forest, so the two best performing models from the two worlds, kind of. And what we see in green is when the DeepSDM is outperforming, so it's the delta in OROC. And in purple, we see the delta if the random forest is doing better. And what we see is that although they are almost at par in the overall OROC, we have a really clear accumulation. I mean, the margins are small. We know we're still talking about a lot of species, but we have the accumulation of where the deep learning-based model is outperforming exactly for those species where we had many papers claim that they act on this. So it's the species that are super infrequent. It's like they live in the lowest 10th percentile of the relative prevalence range. And we see that kind of our assumption of deep learning-based models that train jointly and thereby being able to potentially borrow information from better represented species, at least is reflected in the delta scores that we see here. And then we ran another analysis where we compared our naive deep learning-based baseline to the baseline where we did some simple debiasing strategies. So we did some subsampling and aggregating the species in the 1 kilometer cells. And also here we see that the assumption of this, particularly helping the species that are infrequently sampled and where we have like low sampling effort, is fulfilled. So with this setup, we can kind of break down the overall metric and understand a bit better on which mechanisms during modeling, our model really works. And we also see where we lose some species. And then lastly, I also wanted to show some maps to show that what the models are, what they're producing. So here you see the prediction maps of Brachy's ilex. And yeah, the species lives in the upper right quadrant, so it's like having a very densely sampled range and is very, very well scanned also. And we see the ranking performance is really similar between the two models. But I kind of want to end up by saying, if we look at the maps, they still look very different. So we're not claiming to having solved the evaluation framework, the evaluation problems, but it's rather like really an encouragement to kind of look a bit behind the aggregated metrics. Clearly, these maps, like the ROC, we know it only captures ranking, and we don't see the sharpness in prediction. But it would be really worth to go beyond this. And there might also be different properties that are relevant for different people. Maybe you care more about like niche widths or something, but just to give more space to, looking a bit what properties species share. And yeah, that's with that I stop, and I'm happy to see that.
I have a question. So I really like sort of looking at it from the perspective of prevalence versus sampling, because there's some very rare species that are well sampled, right? And what implications it has. And I'm wondering whether it also can be leveraged for quantifying uncertainty in the outcome.
I think,
knowing that difference between prevalence and sampling effort.
I think yes, because in the end, we still bin a lot of species. Like I said, they are roughly uniformly distributed in the square. And like what you see here is like the 4 main quadrants, so like roughly 1,000 species per square. And then we have the 10th percentile, which is like 200. But we have still a big delta in performance between the species within. So I think it tells us a lot on like how many other factors also work on the OROC score that we can expect, what the ceiling per species kind of is, given the data we have, given the evaluation data we have, and also given kind of how like niche a species occurs and how generalist the species is. But it was one way to kind of break it down a bit, but certainly there's kind of a lot happening under the hood still.
This is really cool. It's funny. We were just talking about this needs to be done. And it's great that you just like did that. So my comment is always kind of the same. You can get the same AUC score, and you can have two models that look entirely different. You give these two models to an expert, and they're like, one's great, one's terrible. You can have the exact same AUC score and have entirely different ranges, if you would estimate the range from the SDM, which is something that they want to do all the time, IUCN, et cetera.
Yeah.
You can have entirely different species richness from two models that have identical AUC scores. And so I guess my question is, could you add a bit to this to just be like, well, what are some other things that we might want to measure, and how does that change? Because I think it might change a lot more than the scores themselves.
I think our goal was to start kind of from what we saw most in the literature being done and kind of being like, hey, maybe deep learning is not the answer to all of this. Maybe we have to look a bit what's happening under the hood. And we are super aware that OROC is really not like telling the whole story. It's like sealing like crazy. I mean, we're talking about deltas of 0.8, like it's really, really small margins. And like all the calibration metrics are not in there yet. But I think we wanted to start with like the basic setup, and the idea is like you can do this with any metric. You can change the axes as you like. Like if you care really more about like niche width, you can put this on the axis. And the idea was more to kind of encourage a breakdown now that we moved to so many species at the same time that, But like, that's why I ended with the maps. I was like, I mean, this already is defeating the story of OROC being the single metric that we should look at. Yeah.
Diego, you had a question maybe?
Just like a curiosity about the data set that you use for evaluation. How is it obtained? Because at the end you showed maps on Quercus ilex.
Yeah.
And like I know with the maps are completely wrong in Spain. It shows like a lot are in Madrid, and then like the whole southwest of Spain is like a Quercus ilex forest, and it appears as like not present.
I mean,
but it's not in the. So I see the Splot open observations. It just has no observations in the south of Spain. That is like a forest of Quercus ilex, basically.
I mean, yeah, we definitely noticed it's, as I said, it's the best evaluation data we could get our hands on for going global. But we train on GBIF data. So the maps come from the GBIF occurrences.
Yeah, but I guess like the GBIF data biases. I mean, it's fine, it's biased, and we know. But the Splot open data, like it also seems to then get like this huge bias, right? Because it's really like a dominant species in like a huge area in southern Portugal and southwest Spain, and it seems not to be present in the green on the Splot open observations. I
think one of the problems that persists is that also Splot open, just like the other data sets that are around, you have very varying plot sizes. So it might be that like particularly there they had like much smaller plot sizes and just like no tree reported in there. Like they say, if they don't state it explicitly, we can expect that the full list of species was checked. But still, I mean, if the plot is really small, what can you expect? So I'm sure, we can only get so far. The ceiling certainly is not at 100, but it's probably much lower depending on the species. And also, it might not reflect the true distribution. Just that's the limitations that we have in the data.
I just have like a very small comment, which is that the map, I think because of the overlay of the plots, it's just really hard to see what the test data is. So maybe if you're presenting it again, you might like disentangle the red, green, and blue and gray plots, at least so they're more comparable. Because I was looking and I was like, wait, like exactly your question, right? Is it that there aren't the green and gray in southern Spain? Or is it that there are, but they're under the red?
Yeah.
I have the same question. So.
Yeah, but also you have to remember Splot, I cannot. Splot open is global, but is sparse also. Like, I cannot scroll. I'm sorry. So in Europe we have the highest density of plots, but
Not in Spain, not
Yeah.
in southern Spain.
So there's also an issue of just like not having plot data available in these areas. So whatever the model does, yeah.
David had a really good point, which would be an awesome baseline to add to, which is just what if you just predict uniformly across that range?
Within a reasonable range.
Within like a reasonable range.
How bad the numbers be?
Like if the aura is like 91,
Yeah.
if you predict uniformly across the range, that feels like it would be a really nice thing to show.
I've been thinking a lot of whether we should add like kind of not measure overall a rock, but rather have like either uniform or KNN based or like an envelope based baseline, and then just look at the deltas actually, because this tells us the true sealing potential of the
Totally.
models.
The goal would be to determine if this is just a bad metric.
Exactly.
Yeah.
Rather than one. Well, it's one of many metrics.
Yeah.
One of many bad measures.
Yeah.
Yeah, on that aspect, I mean, we made some trials. It's really very optimistic.
Yeah.
But also,
We degraded the data to 50% of the data, and it was still nearly the same AUC. So
No, I'm like I started doing some just like KNN experiments of just like take like the distance to the closest PO point and put it in a Gaussian and see. And in data-rich regions, like you definitely perform equally. And overall, like the ceiling is really, really small. You're not talking about like a difference of like 70, but it's much smaller compared to a very simple model. Yeah.
yeah, no, Ocean.
Yes, thanks very much for the talk. It's super cool work. I feel compelled to try and defend the DeepSDM model. So
Sorry.
the part of it is an ensemble of multiple predictors. So if we ensembles
Yeah.
the DeepSDM, do you think you'll squeeze out that tiny little? Not that these circuits mean, but just out of interest.
No, at some point threw together just like somewhere in the middle, we threw together an ensemble and it did give a boost. And you're totally right. Of course, we can expect like some points being gained from that. And I didn't want to say like we shouldn't look at the deep learning models. It's more like I think in this very, very simple setting where the data input sources are really simple and like it's really where the standard models are not like they are not super limited in what they can do. There, I think they are just like performing pretty much similarly. As we see, not for all species. So definitely we should look a bit closer. Yeah.
Thank you.
Yeah, thank you for your presentation. Kind of related to that question, I was wondering what kind of data did you use as input for the DeepSDM and for the random forest? Because also I was surprised by the time it took to train the random forest and.
I mean, it's
yeah.
So we use 52 predictors. I cannot scroll on this. I'm really sorry.
You just pattern light images.
No, we just have tabular inputs. It's so we only like from every kilometer grid cell we just extract the predictor value. It's tabular. It's a vector of 52 variables. It's climate, soil, topography, and human impact variables. And it's just so long because like it's kind of we just like added all the CPU train time per model, but of course, as soon as you have two CPUs, like it's halving. Like we also say it, like it's not meant to be it's not a super fair comparison. You have the GPU for the deep learning models, you have just CPUs. For those models, as soon as you can parallelize, the times shrink a lot. It's just like if you do it naively, that's what you get, kind of.
So maybe I missed it, but what is the loss functions you use for this model? That explains this morning. The choice of the loss function has to be thought according to the utility function you use. And so if you measure species-wide AUC, of course you have to optimize the model with a species-wise loss function.
So we have binary cross per species. That's what we do. And we played around a lot with like how much target group background, how much random background we blend in, and how much do we have to upweight the positives. That's the ablations we did. And in the end, what we found is that target group background alone was actually more expressive than mixing it with random background. And since we did some aggregation and also subsampling of the most prominent species for our final model, we didn't need a super high positive weight either. And in the end, what we did stick with is kind of a per species weight, as proposed by Robin in his paper. So we weight every species' contribution to the loss based on the number of present absences so that everyone receives equal positive and negative feedback.
And regarding the AUC, maybe you should at least measure the sample average AUC, which generally change completely the ranking of the methods. So
yeah.
Okay, any more questions? No, maybe we.
I just have a really quick thing. I don't know what's on the European plots. I guess they're EVA plots, but in the I think most of the US plots are specifically for like community ecology post disturbance.
Mhm.
And so, I mean, maybe just quickly have a look because
Yeah.
that's a very particular application where, you know, you're seeing things on the plots and like they want the time series. And so you have these really ephemeral stuff that comes in and then, you know, a sequence.
Yeah.
So you wouldn't expect that to match the GBIF. So maybe just like
Yeah,
have a look and even kind of like if you could rank them into 3 different kind of ecological situations
I see. Yeah, yeah.
to sort of pull that apart. I know you don't want to go too far down that road, but they are very biased.
No, but that's good to know. Yeah, it's easy to
process.
do.
Yeah.
Thank you.
Thank you again, Emilia.